other words, we have a little proposition, which I'll just write like this. Every smooth variety of dimension d can be embedded in P2d plus 1. So every curve lives in P3, every surface lives in P5. One of the things this should tell you, less with curves than with surfaces, if you have a surface in P3, it's a hypersurface. You knew it was special. If you have a surface in P4, a surface in P4 is already very special. You know that every surface lives in P5, so a surface in P5 isn't very special, 5 or greater. But already here this is telling you that if you find a surface in P4, there should be something interesting about that. Not every surface lives in P4. And similar with higher dimensional objects. Okay, now, I said the dimension, we don't know so much about that. We do know some things. What do we know? We know that if x is a smooth curve, let me put x in Pn. Then this dimension guess is correct. The dimension actually is, so d is 1, 2i plus 1, or n, because at some point you fill up your space. So it's actually the minimum of these two. You can find this in Joe Harris's little book on algebraic geometry. Also in the curve case, once you know the dimension of a variety, maybe you want the degree, very nice argument to tell you the degree of the secant variety to a curve. So how would you find the degree of the first secant variety? You know from the first part that it's three-dimensional. So you have sigma 1 living inside Pn. It's three-dimensional. You want to know the degree, so you intersect it with a general Pn minus 3. Project again. When you intersect with this, so you take this Pn minus 3 and you project, you are now going to project to P2. Because we took a general Pn minus 3, this Pn minus 3 misses the curve. And so the curve will map down very nicely to P2. But what is going to happen every time our hyperplane hits a secant line? This goes back to the first minute and a half of the talk. This hyperplane hits a secant line, the 2 points are going to come together. And we're going to get a cusp down in our node, down in P2. So when we project this curve, really quick, won't happen. We're going to get a bunch of nodes. How many nodes are we going to get? We're going to get the same number of nodes as the degree of the secant variety. So the number of nodes is the degree of the secant variety. But what is the number of nodes to a plane curve? So a very nice simple formula for the degree of the secant variety to a curve. This works just as well as you move up. You want the degree of sigma 2. You intersect with a generic Pn minus 5. You project to P4, and you're counting trisecants in P4. There is a formula for the trisecants of a smooth curve in P4. The formulas get less pretty. And I don't have a closed formula for them, but is computable.
D is the degree of x or degree of D.
Which D?
Okay.
This is the degree of the curve. Yes.
You're using D for dimension.
Yeah. Smooth curve. Yeah. Of
Degree D.
Degree D. I'll put a little hat on it. So it's a different D. Okay. We're good. Now, for the NP property, I told you that NP was not understood for Veronese embeddings of projective space. It is understood that the dimension of the secant varieties are known, but it's fairly recent. Is it? Oh, it's 10 after 3? Oh, no problem. Okay. Theorem of Alexander and Hershowitz from 1996. This says that the dimension of sigma I VDPN is precisely what it should be so it's either our guess or the dimension of the whole space, except in sort of 2 infinities plus 4 cases. So a D, N, and an I. So when do you get something different? When D is 2, quadratic Veronese, these are always the worst things that can happen. So the quadratic Veronese, right? Any theorem on surfaces says the following is true with the exception of the quadratic Veronese in P5. D is 2. This essentially fails all N and all I. Dimension is never right until it fills up the whole space. There are then 4 exceptional cases. 3, 4, 4, 4, 4, 2, 3, 4, 6, 4, 8, 13. Now, it should take a little while about what it would take to figure out that the 13th secant variety to the degree 4 embedding of P4 did not have the dimension you expected it would, but it doesn't. I would say that these examples are all classical. The fact that those did not have the expected dimension has been known forever. The fact that that's all of them is relatively recent. This I'll go ahead and do it. Okay. Why would you be interested in knowing this, aside from the fact that, I don't know, it's interesting. Let me give you a 4-minute introduction to Waring's problem. Waring's problem says this. Suppose you have a homogeneous polynomial. So P. P is a homogeneous polynomial of degree D in n variables. Your job is to rewrite P as a sum of d powers of linear forms. if P is x cubed plus y cubed plus z cubed, P is the sum of powers of linear forms. Less easy if P is x cubed plus 2y squared x plus z cubed. It's not, I don't think it's clear it can be done at first glance. Can you really write this as a sum of cubes of linear terms? You have to play with that a while. And you can sort of overshoot and back up and play with it. But I don't think it's clear that it can be done. But it can be. And not only can it be done, but we know how many terms it takes. Why is that? Well, what is the collection of homogeneous, sums of d powers of linear forms? That is the Veronese embedding. The image of the Veronese embedding is precisely sums of d powers of linear forms. If you want to start adding these things together, you take 2 points on the Veronese and you add them. Think affinely for a minute. 2 points and you add them. You take a point in affine space, point in affine space, and you add those points. You're sitting on the plane that they span. Read projectivizing, you're sitting on the line between them. So the sum of those 2 points lives on the secant line between them. So the question of can you do this and how many different points does it take is simply a question of the dimensions of the secant varieties to the Veronese embeddings. And when do the Veronese variety, the secant varieties fill up the entire space? So this tells you precisely how many of these it takes. It also tells you that the problem is solvable, which I still think isn't obvious. Okay. So a couple last things I want to mention, mostly because I put them in, and now I need to talk about them. Another situation where understanding the dimensions of secant varieties has proved to be very valuable is in the proof of one of Hartshorne's conjectures. So this was 1974. Hartshorne made a pair of conjectures. Suppose xd in Pn is smooth. First, if 3d is greater than 2n, so the dimension is sort of at least 2/3 n, then x is a complete intersection. Second one was that if we weaken this a little bit, 3d is greater than 2n minus 2, then we're not going to have a complete intersection, but this will at least be linearly normal. As we've discussed a little bit, this idea of linear normality is closely related to secant varieties. All right, so let's think about number 2. So if x d in Pn is not linearly normal, what does that tell you? That means it came from Pn plus 1 and we projected down. Right? It means that this xd lived in Pn plus 1 and the first secant variety did not fill up Pn plus 1. Theorem that was proved by Zach in 1979 is precisely that this can't happen. My number's right. So if xd lives in Pn plus 1 and 3d is greater than 2n minus 2, then the secant variety is the whole space. So there is no way to project down.
Pn plus or Pn.
And this, of course, proves part 2 of Hartshorne's conjecture. Zach went further and looked at this border. Said, what if 3d is equal to 2n minus 2? First time 3d is equal to 2n minus 2, d is 2 and n is 4. Yeah, that works. What happens in this case? Well, the theorem holds except in 4 cases. The theorem holds except we have d, we have n. Dimension of sigma 1, 2, 4, 8, 16, 4, 7, 13, 25. There's also 4, 7, 13, 25. 3 of these varieties are sort of very well known. What's the first one? Yes. The worst of all surfaces, the quadratic Veronese, always the exception. Second is P2 cross P2 in P8. Third is G16 lines in P6. It's just the Pluker embedding. The last one is something called the E6 variety and is much less classical. These obviously are very classical. This one a little less so. Let's look very quickly and have a watch. What do you expect the dimensions of the secant varieties to be? In this case, you expect the secant variety to have dimension 5, but it has dimension 4. So this, we say that this has a deficiency of 1. I'll use a little delta here for deficiency. This, the secant variety should have dimension 9. Should be 17, and should be 25 plus 8. So these deficiencies are 1, 2, 4, and 8. This is the most deficient secant variety anybody knows. Smooth, or smooth variety. Nobody knows anything beyond this 8. There is some question as to whether or not a secant variety can be more deficient. I expect the answer is yes. I don't think 8 is a bound in that sense. The problem with finding examples, of course, is the first time you could have a variety whose secant variety had deficiency more than 8, the variety would have to be 19-dimensional. We're not very good at 19-dimensional varieties. I don't know a lot of examples. I know a couple, but I don't know very many. So it becomes difficult to find examples of things that are more deficient because the varieties themselves have to be so large. As long as I put this on the board, let me put a little box around it and say that we don't understand this at all. Even for codimension 2, we have no idea. Are varieties of codimension 2 complete intersections? I know the twisted cubic is not. I know the Horrocks-Mumford surface in P4 is not. I think P1 cross P2 and P5 is not. But that's about it. Once you get to P6 or P7, we don't know. You take something of codimension 2 and P10, is it a complete intersection? Nobody knows. So this conjecture is way wide open. And already 25 years old. 35 years old. Okay.
Okay, thanks very much for your talk.